To build a cyclohexane model, you need 6 sp3 hybridized carbon atoms, the black atoms with 4 prongs, 18 bonds, these are your gray tubes, 12 hydrogen atoms, the white atoms.
Start by connecting the sp3 hybridized carbon atoms in a ring. This ring will have a 3-dimensional structure and will not be able to lay flat on the table.
We will be building the chair conformation of cyclohexane. There are other conformations, such as the boat conformation. But the chair conformation is the most stable because it induces the least strain on the bonds.
It is named a chair conformation because it looks like a lounge chair with a back and footrest.
After creating a ring of carbon atoms, attach 2 more bonds to each carbon. Attach a hydrogen atom on the other end of each bond.
Your structure should stand on 3 legs, with another 3 legs pointing straight up in the air. These are your axial positions. The bonds that alternate pointing slightly up and down around the circle are known as the equatorial positions. You can use different colors for axial and equatorial hydrogens to make it easier to visualize.
Now we are going to perform what is called a ring flip to interconvert the chair model. This is very simple and can be accomplished in a couple of ways.
First way, set your model on the table so the equatorial axis is parallel to the table. The model should be standing on 3 legs.
To perform the flip, take the positions in between the current legs and push down on the equatorial positions.
Second way, take 2 carbon atoms directly opposite each other. Raise one of these atoms above the equatorial plane.
Lower the other atom below the equatorial plane.
Let's repeat this flip with another set of opposing carbon atoms. Raise one above the equatorial plane. Lower the opposite one below the equatorial plane.
When a ring is flipped, the axial substituents will become equatorial and the equatorial substituents will become axial. This is useful when trying to find the most stable conformation of a cyclohexane ring that has substituents on it.
Let's try an example. Find the most stable conformation of trans 1-tertbutyl 3-methylcyclohexane.
We'll start with our basic cyclohexane ring and add a tertbutyl substituent on carbon 1.
For this model to be trans, the substituents need to be pointing in opposite directions. Since we place the tertbutyl in an axial position pointing up, we need to place the methyl on carbon 3 so that it is equatorial pointing down.
Now that we have the model, let's find the most stable conformation. This means that the steric strain is minimized, or that all of the atoms are the furthest away from their neighbors as possible. Currently, the tert-butyl group is pretty close to the other axial atoms. So let's try and do a ring flip and see what happens.
Now the big, bulky tert-butyl group is in the equatorial position, further away from the other atoms. This looks more stable than the other conformation.
In fact, it will always be the case that the cyclohexane will be the most stable when its bulkiest substituents are in the equatorial positions.